Good morning. I'm Sanket Mehrotra, and along with Aniket Tomar and Honko Cleve, I would like to start our CS535 Big Data Project presentation on COVID-19 literature clustering. In response to the coronavirus pandemic, the White House has released a continuously evolving dataset of a collection of papers about COVID-19, SARS coronavirus 2, and other related coronaviruses. There are thousands of papers published about this topic in the past few years, and even more being released today. We asked the question, would it be faster and easier for scientists to do their research if they knew what papers were related to the one they're interested in? Paper abstracts are a short overview of the whole paper. They are comparably similar in papers talking about the same subject. We use this observation to cluster the published articles in the CORD dataset and apply topic modeling to identify which terms best describe an abstract of the paper.
Hi, I'm Aniket and I will be talking about our methodology to solve the problem. Our general approach in the project involves the following steps. First, we parse the text from the body of each document using natural language processing techniques. Then, we turn each document into a feature vector using the TF-IDF method. In TF-IDF, for each word in a document, we calculate a score that captures its significance in the document's word embedding. We do this by multiplying the word's frequency in the document with the inverse of its frequency in the entire corpus. This inverse frequency gives us how informative the word is. After this step, we get a vector for each document with length equal to the number of unique words in the corpus. Then, we run principal component analysis or PCA to reduce the number of dimensions to make the data more manageable and reduce the training time of our machine learning algorithms. This will also reduce the noise and outliers in the embedding, which will result in better clustering. Then, after this, we use PySpark's implementation of distributed k-means plus algorithm to cluster the data. Here, we use the elbow method and the silhouette method to validate and evaluate the clustering. We'll talk more about this later. We also use a distributed MLP classifier to classify documents with the clusters resulting from k-means as their target classes. If a classifier can predict the correct class of documents well, then it means that the k-means clustering did actually capture some meaningful relationship between the documents. After clustering the data and evaluating the clustering, we need to reduce the dimensionality to 2D and plot the clusters. For this, we use t-SNE instead of the already calculated PCA because unlike PCA, t-SNE reduces the dimensionality while also trying to keep similar instances close and dissimilar instances apart. It is therefore particularly well suited for visualizing clusters of data. A comparison between PCA's scatterplot and t-SNE's scatterplot on unlabeled data is shown here. Also, visually inspecting t-SNE's scatterplot on data labeled with clusters, it appears that the data points are plotted in a close resemblance to their corresponding clusters. The largest chunk of runtime in our project was due to t-SNE because we couldn't run a distributed t-SNE as PySpark doesn't provide an implementation for it. Also, we had to run it multiple times because t-SNE is very sensitive to a number of its parameters such as perplexity and learning rate, and therefore much experimentation is needed to get appropriate values for these parameters. Next, we use latent dirichlet allocation or LDA for topic modeling. This step will assign topics to each cluster, making the clusters more informative. In LDA, each topic represents a set of words, and the goal is to map all the documents to the topics in a way such that the words in each document are mostly captured by those topics. Finally, we make the plot interactive using bokeh. So now, while we are exploring similar articles, we can zoom in to get articles that are more closely related and zoom out to get a high level overview.
This project led us to explore several great libraries to get to our goal. Here are a list of packages we used to build our tool. Since we implemented clustering in LDA with both PySpark and scikit-learn, we could contrast the performance gains in using each package in both a distributed and non-distributed fashion. PySpark worked great for the LDA and vectorizing, and its k-means plus plus parallel implementation was quick too. On the other hand, scikit-learn's k-means plus plus and tsne implementations took a much longer time to run, taking upwards of 45 minutes on just one-fourth of the dataset. SpaceC was used because it contained a parser specifically for clinical and biological texts and contained several more relevant stop words for us to clean the text with. HDFS was used to read data from our Hadoop cluster, and Task was used to try and distribute scikit-learn's computations to make it faster. Both word-cloud and TQDM were used for visualizations and progress bars, respectively.
How can we evaluate the models are well partitioned based on different k? We use two methods. First, elbow method. The sum of scale distances of each point from the centroid of the cluster suggests the proper number of cluster k. We evaluated SSE using Spark for different values of k from 2 to 49 and found a good k value where the curve formed an elbow and flattened out. The elbow plot illustrates the point starting at 6, flattened out and forming an elbow despite the cost at A spiked up once. However, this method does not always give a good k value. The elbow point is sometimes ambiguous. Thus, we also consider silhouette analysis. Silhouetry can be used to determine the degree of separation between clusters. This method computes coefficients with all points in the same cluster and closest cluster. The result of the coefficients is between -1 and 1. The score near 1 indicates that the sample is far away from the neighboring clusters. On the other hand, close to 0 indicates the sample is close to the neighboring clusters. Negative is it assigned to the wrong clusters. Therefore, we should find silhouette score as close to 1 as possible. In this project, Spark and scikit-learn used to analyze silhouetry for an optimal value of clusters. First, we computed silhouette coefficients with Spark. This table shows that the average of coefficients by descending order with the number of clusters. The number of clusters at 2 has the closest value to 1. Can we select 2 for the optimal cluster? It seemed plausible. To make sure, we further explored silhouette analysis with scikit-learn. Surprisingly, coefficients had been increased by reaching the number of clusters at 47 after 2. Also, the thickness of silhouette plot showed good shape. Therefore, cluster of 2 was reasonable at the first time, but now 47 was more credible. Yet 47 took more time to cluster it.
We'd like to conclude our presentation with a list of what we think we liked about our project, what we didn't like, and future work which can be used to extend our project. In the pros, we implemented and experimented with a distributed document clustering approach. Secondly, we used PySpark, which allowed us to deploy our computations over a cluster and increase the speed of computations, which otherwise were taking very long with scikit-learn. Uh, Thirdly, we ran LDA over all the abstracts in our corpus and managed to associate them with their cluster. Thus, allowing us to be able to group the list of tags or keywords that can be used to describe a cluster. And the cons, we we felt more fine-tuning of our clustering was required. The results of the elbow plot and the silhouette analysis indicated that for up to 47 or 50 clusters were optimum given our data set. But running those computations took a long time, almost too long for us to be able to submit it in time. Also, the dataset we were given had several useful features or columns that we could have used to aid our clustering, such as authors, date of publishing, and reference papers for a given paper. And we didn't get to use those. Finally, for future work, we'd like to implement a search interface which allows you to input a search query and will return the most relevant cluster of papers for your query. And apart from the abstracts, we would also like to apply these methods on the body of articles. And thirdly, we'd like to merge the outputs of the LDA and clustering into our interactive plot so that you can, in our interactive plot, you can click on a cluster and see the keywords associated with it. These are our resources and references. And thank you very much for watching.